First.
Let's go.
All right. Hello, everybody. This is our third ACES seminar of the first half of this year and the second to last of ACES 1.0. I'd first like to recognize the traditional owners of the countries where we all work today and the First Nations people present in this webinar or meeting, and I'd like to pay my respects to elders past and present. So today we've got Benoit Pasquier, who is a mathematically trained oceanographer and currently a research associate at the Climate Change Research Centre in Sydney. His expertise lies in combining inverse modelling, transport matrix methods, and green function-based diagnostics with ocean models and archives to quantify how ventilation, sequestration, and biological pumps respond to a warming, slowing ocean. So please, Benoit, take away.
Thank you. Thank you, Matt. Thank you for letting me present on this work. This is a bit of a sad presentation in a sense because it's not finished work, and I usually don't do that. I'm okay with presenting unpublished work, but this feels like it needs probably another 6 months of work to be really ready for a nice presentation. But it's still interesting, I think, and I still wanted to give a talk about this work before my contract ends, which is soon. And so this is about bringing these tools, transport matrices, and offline models to high resolution models. And as I said, it's not finished, and that's why it's still an ongoing journey. I've gotten help from all these wonderful people listed at the bottom. There's Laurie Manviel, my supervisor. There's Greg Wagner and Simone Silvestri that are developers of Oceananigans, and I'll talk about that a bit later, why I use that. There's Alexis Montoison, who's like a GPU expert who helped me a bit with that. There's Taimur, that you may know well, who's helped me with Oceananigans and GPU. Andrew Keys for lots of access to M2 little details and tidbits where he helped. And François Primo for most of the mathematics that underlie all this work. So the context of this project is to look in particular at the Southern Ocean. The Southern Ocean is, I'm sure you know, very important for the storage of heat, of carbon, and for oxygen levels in the ocean. Part of it is because it's a major gateway to the deep ocean, in particular through Antarctic bottom water. So these formations of very dense waters that go very deep and stay in the deep ocean for a very long time. And here, timescales, we are thinking about timescales of hundreds to thousands of years, thousands plural. And so these are really important for very long timescales compared to, say, what we think about climate change these days in terms of maybe a couple of decades. This is more important for the longer term than that. But it's still very important because the future ocean and the future climate will depend on how the ocean circulates carbon and heat, and life will depend on how it circulates oxygen. On the right, there's like a schematic from Wikipedia about the Great Ocean Conveyor Belt. It's not very accurate, but it sort of shows the general pattern and that purple flow going down near the Antarctica into those blue arrows, which are supposed to represent the deep currents. I apologize for my voice. I'm a bit sick, obviously. You'll have to suffer through the sound of sickness. Um, there were two very interesting studies from colleagues in Australia that used high resolution access OM2 models to look at how this deep water would change with different forcings. There was one where they altered Antarctic meltwater, and so how this affected the abyssal overturning, and then another set of experiments where they changed the winds, the local winds, and this also affects how these deep waters form. And so the idea is that these studies are really interesting, but there is one thing they can't do is they can't look at the very long-term impact. And that's because at high resolution, there is a cost to run simulations for long times that is just too expensive. And I'll come back to it. Um, why do we need high resolutions for these questions? I'm sure some people in the audience can explain it better than me, but there's this very nice video put up by ACEAS NRI where they show this dense shelf water forming near Antarctica and how it sinks along the continental slope. And if you look at it, you can really understand how fine the resolution must be to capture this transport that is really local, really along the continental slope. And of course, if you go to quarter or 1 degree or even 2 degree resolution, you will never capture those dense shelf waters forming. So in general, coarse resolution models work around this by having open ocean convection and very deep mixed layers to represent this transport, but it's not realistic. It has a ton of features that you probably don't want to see, and so that's why we want to target high resolution. Um, that's Sorry, that's not been updated. I made it on another computer. I'll skip that. So this is the cost, estimated cost that you would need if you wanted to run those models to equilibrium. So ACEAS OM2 comes with 3 resolutions, 1 degree, quarter degree, 0.1 degree. I found some benchmarks online and in papers. The original paper by Andrew describing the model has some benchmarks in there, and I found some on the Access Hive forum for costs. And on the right-hand side, I want to draw your attention to how much it would cost in time and in service units. So this is the currency. This is the currency of running models on GADI if we wanted to run it to equilibrium. And so typical timescale for that is 3,000 years. And for Access OM2.1, so the coarser version, it would take about 60 days, which is about 2 months. For Access OM2.01, the high resolution version, it would take about 7 years. And that's if everything worked perfectly and you didn't have to deal with shenanigans, with memory, with stringing different jobs efficiently. There's no extra wait time. And so it's absolutely not something anybody wants to do for a research project. And in terms of costs, this is also way too big, in particular for Access OM2 high resolution, 0.1 degree. It would take about 500 million service units, which is way too much. I don't even know if they allocate that in the entirety of NCI every 7 years. So it just is completely infeasible. We need another way to spin up and accelerate those tracers if we want to have an experiment where we can look at the age of water and tracers that represent ventilation on long timescales. So I mentioned transport matrices, and I probably need to explain a little bit about what this is. Transport matrices are representations of the ocean circulation and the local sources and sinks. And this is a tiny shoebox example to explain what I mean by that. So it's a 2x2, very, very coarse ocean model representation. There's some overturning represented. I can't see my own mouse, so I can't see my cursor. But you can see there's an overturning. There is a circumpolar current with that long blue arrow. And what this means is, oh, I do see my cursor. When we say we're going to use a transport matrix, is that we are simply rearranging the 3D array of the tracer, the 3D grid of the model, into a one D column vector. And when we do that, all the processes that are linear, like the advection transport, which is, can you see my cursor, just to be sure? Yeah, like the advection term here, this is typically a term that is linear in concentration, depending on your advection scheme, your diffusion scheme. The whole transport, this is diffusion, can be linear, and something that is linear and that acts on a vector can be represented as a matrix. So that's what the transport matrix is. So I'm realizing this is not the latest presentation, but I'll move on. Sorry, shortcuts appeared. I don't know if you saw that. And so we can't use direct time stepping because of a barrier, a physical or computational barrier to the efficiency of time stepping models at high resolution. It's typically captured by what is called the CFL condition, for Courant-Friedrich-Lewy condition, and it's a limit on how big a time step can be. Because the time stepping in models has to be explicit, and that is fundamentally unstable if the time step is too large. And so what we do here with our transport matrices is we can do two things. We can, first of all, do implicit time steps, and we're not going into the details of what that means, but essentially we solve for a linear system. And then that condition breaks, and we can have very large time steps on the order of months or even years, and that can accelerate things dramatically. But even better, we can directly solve for the steady or the periodic state and avoid time stepping altogether. So you can use Newton's method for nonlinear problems, and you can use direct matrix inversions for linear problems. And this works really well in theory. In theory, because within this framework, you need to solve a linear system, and direct linear system solvers do not scale well with resolution, with size. They actually scale really bad with it, order n square or n cube for models or matrices of size n. So to give you an example, the transport matrix that we can build for access OM to 1 degree, which is the coarser version, is already on the more expensive side of transport matrices that we use in general. It takes about, I would say, 100 gigabytes of memory to build the factors, and to solve it takes about 20 minutes with the default solvers you can find in MATLAB or Julia, for example. If we move on to access OM to 0.1 degree, which is 150 times bigger in terms of number of grid cells that are a part of the ocean model, that means squaring or cubing that number in terms of resources required to use the transport matrix. So it's 20,000 times to 3 million times more expensive. And that's, again, something you can't do. You're dead if you try to do that. You need another way to deal with this problem. And the other way is to use an iterative solver, also known as Krylov subspace methods. And these allow you to solve for very, very large systems, where even systems where you can't even build the matrix itself or store it. And that's what we are using here. So this is a schematic of what I do. And I'm going to take you around starting from the bottom. I lost my cursor again. I'll try to do it without the cursor. At the bottom, you have this blue little box. I'm going to use Oceananigans. Why Oceananigans? Well, I'm already extracting output from archives of AccessOM2 experiments. I don't really need to rerun AccessOM2. And so I thought I'm going to run a model that's faster, and Oceananigans is faster because it can run on GPUs already. Maybe in the future we'll have a GPU version of AccessOM2, and that will be great, avoid me all this work, but I thought that was the solution for it. And I'm going to run a single year that is going to be always the same year of circulation. So the velocities are always the same, taken from monthly outputs. So I don't touch the velocities, and I only simulate the age tracer embedded in those velocity fields. This is this phi function here. It's a map. It's going to map the age at a certain time to the age a year later. And then I'm going to look at the drift over that 1 year. And I call this function G. That's the slightly bigger bluish, greenish square. I'm looking at the drift. So I'm just taking the map to after 1 year and subtracting the age I started with. So I take an age, any given estimate of the age that I have, simulate the age for 1 year, see how it's changed. And the goal is to make sure this drift is zero. That is, that the age after 1 year simulation is back to its original state. To give you an idea of how fast this goes, for the output from OM to 1, so the 1 degree version, it takes about 30 seconds to do 1 year. So that's much faster than the original online Access OM2.1, and that's why I use this technique. For Access OM2.01, for the high resolution, it's about 1 hour for a full year. Once I've done that, I need to linearize or convert this 3D array of the age into a column vector that I mentioned earlier. And then I'm going to apply Newton's method to this G map. Newton's method trying to solve for the root of the G function, which is going to find me the age that repeats itself every year. To do that, I need to compute this J inverse times G of A that I circled here, and that points to this pink square. And there's a problem here. There's many problems, but one of the big problems is that J itself is big and dense. And I apologize for any J's in the room. What I mean by that is that J here is the Jacobian of this G function. It's going to be a large matrix, and every entry is going to be non-zero if there's a connection between a grid cell A and grid cell B. And after a full year of simulation, every cell affects every cell. So that matrix, even for the coarse resolution, is going to be 3 million times 3 million of floating point entries. It doesn't fit in any memory, in any computer, even on GADI, on the largest queues. It doesn't even fit in there. So we can't do that. So instead, we use an iterative solver, the Krylov method that I mentioned earlier. Specifically, we use the GMRES algorithm, and that allows us to not build this J, but we do need to give it an approximation of the inverse. And for the approximation, we do two things. The first thing is we take an instantaneous J. That means we take only the average of the Jacobian of the tendency at each time step. So after one time step, the dependencies between grid cells is just the neighbors. Only the neighbors affect the cell you are looking at, because there's some advection scheme, some diffusion scheme, but it only involves the local neighbors. And that means the Jacobian matrix will be pretty sparse, lots of zeros. So that's a good thing, and it's an approximation, of course, but it works pretty well. And so we take a mean of the tendency over the year, and we take that as our approximate Jacobian. The other thing we need to do, because this J, despite being sparse, is still too big, is we need to coarsen it. And so to do that, we just lump grid cells 2 by 2 or 3 by 3 or 4 by 4 and so on into a coarser grid and apply our matrix there where we actually solve with the direct solver, and then lump it back, spray it back onto the finer grid. And this whole setup was already designed by Bardin and Primo back in 2014, but it had never been applied in this context of high resolution. So this still is a bit new. To give you an idea also of how long this takes to run, For a OM21, so the 1 degree version, it takes about 30 seconds per year simulation, and it takes about 70 times this loop to get to a converged state. So it takes about 70 years only to do the equivalent of 3,000 years of simulation. And for OM2 quarter degree, it takes about 120 evaluations. For the OM2 0.1 degree, I don't know because I haven't managed to pull this off yet. But I'm thinking it takes on the order of 100 or so iterates. So what did I actually do? I grabbed the basic simulations of OM2. Lost my light. Okay. Um, I took the basic interannually forced simulations of OM2 at different resolutions, and I looked at Antarctic bottom water and North Atlantic deep water. So these are the time series shown on the right for the two resolutions and for the two deep waters. And I decided to grab some decades that had some sort of extreme values for these waters to compare the effect of this internal variability along that IAF time period. And I'm going to just run this whole pipeline, look at the age, look at the age, and also look at the ventilation patterns of the ocean and do some cross comparisons. So here are maps of the age, the ideal age at 2,000 meters. On each row, the first two rows, you have the two resolution, the two rows, you have the two time periods, so the early period and the later period. On the two columns are the two resolutions, and the third row and third column are the difference plots. So there's a few things to talk about here. I'll try to tell you what I've seen, what I've spotted. This is very fresh, so there's probably things that I haven't understood or thought carefully about. And I'm happy to have long discussions about how to explain all these patterns. One thing that I think is interesting to spot is first going to the right. If you increase resolution, you can tell right away that the two different plots are completely different, or not complete. They share some similarities, and there are some parts that are different. The obvious part that really shows is that North Pacific signal, there's a large increase in the age going to high resolution for the earlier time period, time window. There's not such a large increase for the other time window. So that means that increasing resolution has different effects at different periods of that time window. And so it's just important to note that it's not systematically going to, increase the age in the North Pacific. It really depends on the forcing, the winds, and the state of the velocities that you're comparing to. There's also quite a different pattern in the Atlantic, with an increase in age for the earlier period in the North Atlantic and a decrease near the west coast of Africa, and apparently almost no signal in the later period. If you look at finer details, for example, near Sri Lanka or near the east coast of Australia, you see some patterns that seem to be consistent across those two comparisons with a large decrease in age. And that might be because the finer resolution resolves some of the finer details of the current system there. And so maybe that is systematic and robust, and there's something to be said about the higher resolution in these regions. If you look at now the other direction, the change in time windows, to look at the internal variability, if you will, you also see completely different pictures with, in some cases, large increases in the North Pacific for the OM21, which we don't see for the OM2 quarter degree. We also see a large decrease in the west coast of Africa that we don't see in quarter degree. I mean, there's lots of information here, and you see some increase in age right in the deep water formation region, just for the quarter degree. That is not nearly as strong for the 1 degree map. Okay, I don't want to spend too much time on this. There's a lot of detail to look at here. I'm going to move on to zonal averages um, in the interest of time. Same layout. So columns are resolutions, rows are time windows, and you can look at the differences on the third row and third column. I'm not going to look at the difference plots here, but if you look at the second time window, so the second row, you can maybe spot, for example, this is the Atlantic zonal mean I should have mentioned. So we've got depth on the y-axis and latitude on the x-axis. And you can maybe see a signal of stronger North Atlantic deep water entering southward for the second row than you see in the first row. You can also notice some differences in how deep North Atlantic deep water reaches the seafloor right at 60 North, which varies both with time window and resolution. So it increases with higher resolution, that red blob on the right column, and it decreases with the time window only for the quarter degree. So completely non-systematic patterns here that are really telling of how sensitive these water masses and how they form are to the surface forcing and to the resolution. I move on to the Pacific. Very large differences, in particular in terms of magnitude. If you look at the quarter degree version is much older, not everywhere. It's much older in the those deep waters of the shadow zones of the Pacific, particularly in the second time window. There's a downward shift as well with resolution. The deep patterns in the Pacific are quite different, and I suspect it's because the pathways, the three-dimensional pathways, are not the same. If maybe you noticed in the maps, the slices at 2,000 meters, that there was already some patterns here that were different, and I think maybe something is happening on the abyssal currents there as well. And I don't have much more explanation for this. I'm not entirely sure what causes all these patterns. Interestingly, you can see that increasing resolution, you see maybe a bit less of age in the intermediate and mode water region, and maybe this is because there's a finer resolution has this effect. I'm not too sure. So if the age is younger, it means that there's stronger flow of intermediate and mode waters, and maybe a weaker flow of bottom waters. We see similar pattern for the Indian, so I'm going to skip that, and I'm going to show you maps of ventilation. And I apologize for this. I'm going to remove it right away. So these are maps of ventilation. The top row is the first time window. The second one is the difference plot between the two time windows, where purple means a decrease and green means an increase. So you can think of those as the map of the volume that is ventilated per pixel, per unit area. This is why you sort of see the deep water mass formations showing up, the intermediate and mode water formation regions showing up. You can see very cleanly the North Atlantic deep water formation regions, Nordic Sea, Labrador Sea, and so on. And on the right, that profile is a zonal integral of these maps. And you can also tell that there's those different water masses being formed. So these diagnostics are really cheap to do once you have the uh, time to reemergence, which is sort of the inverse of the or adjoint of the age, and we can go into that during the questions if you want to know how to do it. And these, I think, are the most revealing diagnostic to understand what ventilates or where is the ocean ventilated. If you look at the pattern of the difference, it's quite interesting. You've got generally a decrease in the Southern Ocean deep water formation, and globally integrated, an increase in North Atlantic deep water formation. So the ocean ventilation pattern has changed quite a bit. Um, what's also interesting is that the pattern within the Southern Ocean change and within the Antarctic change is also not systematic in the sense that you've got less Nordic Sea contributing to the North Atlantic deep water, but more in the Labrador Sea, and same along the coast of the Southern Ocean, on the Ross Sea and the Weddell Sea, you see some shifts of where most of that water ventilates the ocean. And then there's also some changes in intermediate and mode waters that are a bit less important. And if I move on, so that was, I should have mentioned, that was for 1 degree version. If I move on to quarter degree, what strikes me is that the patterns are really, really similar. There's a bit of a difference in that there's less deep water formation in the Southern Ocean and in the North Atlantic, and there's more contributions from intermediate and mode waters. So the ventilation of the ocean is a bit different between the two resolutions, but the pattern of the change across time windows is quite similar. We have a decrease in Southern Ocean deep water, an increase overall in North Atlantic deep water, and those shifts are also similar, with a shift from the Nordic Sea to the Labrador Sea and a shift eastward in the Weddell Sea. Okay. Okay, I'm going to go to conclude on the times that these experiments took. So uh, discounting the time that it took me to code this all up and make these plots, of course. If you want to solve for the access OM to one age, which allows me to do all these plots, it takes about 20 minutes. And so that compares really well against the 60 days that it would take to run the full access OM2 model. It's a saving of about, that's what's shown in that green box. It's a saving of about 4,500 times. It's significant. In terms of service units, it's dramatically more important. It's about 10 SUs. That compares really well to the 3,000 KSUs that you would need to run Access OM2 for 3,000 years. The order of savings is 300,000. So that's really unbeatable. There are other methods to accelerate spin-ups. There's one that we should definitely start using, which is called Anderson acceleration, which has a lot of advantages, and it typically gets you about 10x to 20x, maybe 50x savings in both speed up and resources. But this approach here is dramatically more efficient if it works, of course. For quarter degree, it takes about 5 hours to find a solution, which is a lot better than a full year. And the resource savings are also still quite significant, order tens of thousands. And for Access OM2 at 0.1 degree, I don't know. I'm hoping that I can get a solution in a couple of days, which would still be much, much faster than waiting 7 years or 10 years. And the resource savings will still be very, very significant if it works, of course. So this is the big goal here. The goal is to apply this method to those studies, to those experiments where the driving force is the drivers of Antarctic bottom water, like wind and meltwater, have been altered, so we can see the long-term effects of these perturbations with an equilibrated age and look at ventilation diagnostics this way. That would be amazing. Um, and so I have some runs currently trying to do that. And I have some ideas of how to get there. And this will be my last slide. Uh, my last attempt failed after a 48-hour job on 4 GPUs with a 5x5 coarsening. The 5x5 coarsening is maybe too coarse, and so maybe the Jacobian is too approximate. That means that the GMRes, the Krylov solver, takes a bit too much time, too many iterates, too many maps of 1 year, too many simulations of 1 year to get one iterate done. So I'm currently running 4x4, crossing my fingers that it works. It's in the middle of the run. It takes a bit of time to get on those GPU queues on Gadi because they are quite in demand. So this is also a bit slowing down the progress. One issue that I have is that have not been able to scale up to more than 4 GPUs. I think if I could double the GPUs, I could essentially half the time that it takes, and that would make probably this more practical and realistic, that it actually converges. Um, it's not that I haven't been able to run it on 8 GPUs, it's that it just doesn't scale. So it just takes as long as it does on 4 GPUs. So I think that's an MPI, software developer job almost, and I'm struggling with that quite a bit. But it would be great if I could get that to work. And yeah, and if you have any ideas, of course, I'm more than keen to try them. And that's it. That's all I have for you. I hope it wasn't too messy. I apologize. I didn't upload my latest slides. They're on the other laptop, so there's a bit of a shenanigans there. Um, but yeah, let me know if you have any questions, anything that was confusing. I'm happy to explain.
Benoit, does anyone have any questions? Oh, David?
Yeah, so lots of great stuff in there. I'm I'm sorry, I had a few things that I wanted to ask about. So how do you get the transports into oceananigans? Is it like just saving the advection field somehow and just pretending that they came from oceananigans model? Can you sort of bypass some aspect of it?
Yeah, so it's definitely not apples to apples. I just grab the mass transports, and then from those mass transports and from the evolution of the sea surface height, I recalculate the velocities, uh, and then I use also the vertical velocity from ACEAS-OM2. So these are monthly outputs that are saved in the archives on Gadi on NCI's servers. They're probably also available in other nodes I'm not sure. But I just load those archives, transform them into Oceananigan friendly grid, which matches the ACEAS-OM grid, but it's a different language, it's a different grid. I spent quite a bit of time making it work for the tripolar seam. That was a bit of a pain. So ACEAS-OM2 has this tripolar grid where you have to be really careful of how you connect in the North Pole, because there's the grid folds onto itself. And then I run um, Oceananigans offline, as in it interpolates between those monthly averages, the velocities, and the tracer flows along those. I add a bit of diffusion by hand, and the advection scheme is different, the diffusion scheme is different. There's the time step is different. I try to crank it up as much as I can. Um, yeah, so it's a bit different.
Any other questions?
I have more, but I want to give others a chance to ask.
I'll ask a quick one. Thanks, Benoit. As a paleo person, maybe I'm looking at it from a different angle, and I don't know much about this kind of things, but can you get some idea of like these ventilation processes on longer timescales? You're talking about, it takes thousands of years for the overturning to occur, but the time slices that you used as examples were kind of in the last 100 years. Can you break that and go in like longer term backwards or longer term forwards kind of timescales?
Yeah, so it's a good question because it's a bit of an idealized experiment in that I take a decadal snapshot of the ocean and then I work as if that circulation doesn't change for millennia or for perpetuity, actually. And so, in a sense, I'm already doing the very, very long time scales. And you can decompose the signal as well. You could, do some extra simulations where you look at the time-dependent transit times, and you can see the full distribution of times of how much you can decompose the age into time distributions. Sorry, I've got the light going off again. Um, but it is constrained by the outputs that are available, and the outputs that are available to me are the ones that are put out and archived by people who run simulations with Access OM2. So these were using the IAF interannual forcing simulations, which run between 1960 and 2020 approximately. And so that's the window of ocean states that I can work with. Um, if you're talking about climate models and Earth system models, there are other simulations, and David, for example, has built simulations of the Miocene and of much different climates on much different um, timescales, geological timescales. But these are doable, but I need to have the archives that already exist so that I can grab the snapshot of the ocean state and the velocities.
You want to ask another one, David?
Yeah, so I was actually just wondering if you decided that the tenth of degree model was just you couldn't you couldn't get the memory and stuff to work. Could you just say, all right, fine, we'll take our diagnostics, we'll halve the resolution using whatever is the most appropriate way, and you say, all right, now we have like a 0.2 degree model, which is based on the dynamics of a 0.1 degree model, and then use that as your basis for a solution the same way.
Yeah, I guess it's possible. But I think the devil is in the detail, and I don't know exactly how I would go about doing that, and it would not if it would work, and if it works, wouldn't it be the same requirements that what I'm doing right now? Because I have a bit of this idea of coarsening already baked in through that preconditioning. And so, yeah, I'm unsure what other strategies would work. But yes, if 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 we can make it work, and there's a hard limit to how high a resolution we can use, then we should try the highest resolution we can get. So far, it's quarter degree, um, and we'll see. Maybe we can push even further than 0.1 degree if we fix some problem. Maybe it's not the right linear solver that I'm using. Maybe I can use a less coarsening myself in the matrix. So there's one issue, for example, right now is that I run the high resolution model on 4 GPUs. And those GPUs then gather the 3D array that is partitioned into 4 ranks into a single column vector that is on one rank only. And that one rank is going to do all the matrix stuff. And so that one rank has only a quarter of the memory for the CPUs that the node has. So maybe somebody really good with, those architecture things can help me get more memory on that rank for the CPU. And then I can maybe have a less coarsening, say 3 by 3, and maybe that will work. I don't know. Like the real struggle I've had with this is that I've hit a bunch of times really like developer problems that are a bit beyond my skill level, my pay grade. And so I've managed to get around a few of those problems, but others I haven't been able to. Like using multiple GPUs worked after quite a bit of work, but then going to multiple nodes. So every node on Gaudi GPU node has 4 GPUs. So if you want to use 8, you need to have some communication between nodes, and I haven't set that up correctly. So that would be great. I think that would help a lot. If I could also deal with the memory of the CPU of the rank that does the matrix stuff, that would be great. Because the GPUs have their own RAM, the CPUs have their own RAM, and they all work together. But I don't need any RAM from the CPUs when I run Oceananigans, because Oceananigans run only on the GPUs. So I could maybe, get more out of the same setup if I could fine tune, I guess, how the architecture works for me. But this is not my expertise. This is not my skill. So I'm like a bit lost on how to tackle these problems. Um, so I try, and so far I've succeeded at like 2/3 of it, and I'm missing a last bit.
Cool. Just before I sign off, I would just say that your 3,000 year estimate is too modest. So the savings that you're quoting, you could beef those up because I've run models for 5,000 years and the age trace is still not in equilibrium, right? It's good enough because it's 5,000 years and you've got to write up the paper, right? But 3,000 years will not get your age tracer in equilibrium. So, maybe add another factor of 2 or something.
Do you want to go, Carl? I see
Yeah,
your hand is up. Yeah.
I might ask, but it just strikes me we need computer science expertise in ACEAS as well. Um, just wondering, I think one of your first slides was an ocean overturning model or figure. As an output for ACEAS, it would be good to update that on Wikipedia somewhere. I've just been looking around Wikipedia. I can't see where that is. So if you could shoot through a link, I might have a go at
Um,
dealing with the Wikipedia editing community and see if we can update our own
Yeah,
figure.
I forgot where I got it. I think it was Wikipedia. It might have been just Wikimedia Commons or something. I just typed overturning um, online. I added the black part because it's like a transparent GIF. But yeah, it looks like uh, maybe I can show you. Just in case you look for it, it's just this part.
Yep. Yeah, sure.
Um,
I think Gabriel Pontes would be very happy if he made it onto Wikipedia. Yeah, thanks, Benoit.
You're welcome. Thank you for having me.
There are no more questions. Thank you so much, Benoit, for your talk today. It was really good.
Thank you. See you.
We've got one more AC seminar, which is on the 22nd of June at lunchtime, and that'll be hosted at IMAS. So you should be getting bookings for that coming through soon. Okay. Thanks, everybody.
Thanks, Matt.
Thank you, Matt.
Thanks, Benoit.